Good afternoon, everyone. Today we'll do the second hardware experiment of your EMW, that is to determine the frequency and wavelength in a rectangular waveguide working in TE10 mode. That means here we'll find the frequency and wavelength of the rectangular waveguide. Here the objective is we'll first find theoretically the frequency and wavelength, and practically we'll find the frequency and wavelength. Then we'll calculate the percentage of error. Okay. What is a waveguide? You can see this is a waveguide. This is a waveguide in air traffic control radar. This one is a waveguide. I can show you, and you can see this one. You can see this one. This is a rectangular waveguide. If I actually this is a SS tuner. This is also a waveguide. If I remove this, you can see this is a rectangular shape waveguide. This length is A, this breadth is B, and since it guides the electromagnetic wave, that's why its name is waveguide. This is also like a transmission line where the electromagnetic wave can propagate. This is the length A, this is the width B. You can see this picture. This is a waveguide. The broader dimension is A, the narrow dimension is B. This is a waveguide used in radar. That means the radar is excited, or the signal is given to the radar by this waveguide. These are the equipments required. Your Klystron power supply. The Klystron tube is the microwave source. To excite the source, to generate the source, we need a Klystron power supply. It gives the beam voltage, repeller voltage, current by this Klystron power supply. Then we have this isolator and frequency meter, variable attenuator, slotted section, tunable probe, waveguide stand, SWR meter, match termination. All these things I will tell you in the microwave test bench. I will show you what is the function of each equipments. Then how this before going to the practical, I will give you some theory. Actually, this rectangular waveguide is in your fifth module. The fourth module is your transmission line. The fifth module is your rectangular waveguide. In that case, I will teach all these things, how this how the wave propagate in a rectangular waveguide. First, I will take the Maxwell's equations, and rearranging the Maxwell's equation, you will get the wave equation, that is Helmholtz wave equation. When you solve that wave equation, you get its solution. After you getting the solution, you have to put the boundary condition. For a rectangular waveguide, you have to put the boundary condition along its walls. That means top wall, bottom wall, side wall, this side wall. After putting the boundary conditions, you will get the transmission in rectangular waveguide. So see, there are different modes, and each mode has its cutoff frequency. What is a mode? What is its cutoff frequency? We will study in your fifth module. Let me show you what is the mode. See, this is the TE mode. Different types of modes are there. Transverse electric mode, transverse magnetic mode. In TE mode, transverse electric. In transverse, you have three modes: TEM mode, TE mode, TEM mode. In transverse electromagnetic mode, the electric field, magnetic field, and the direction of propagation are perpendicular to each other. Suppose this is the Z direction, where the wave propagates, and suppose this is the x-axis, this is the y-axis, this is the z-axis. The electric field, suppose this is the x-axis, the electric field is varying in this x-axis, up and down, and move along z direction. And this is suppose magnetic field. Magnetic field varies in the y-axis, and both are propagating in the z direction. That is the TEM mode, transverse electromagnetic mode. That means electric field, magnetic field, and both are perpendicular to the direction of propagation. It is the TEM mode. In transverse electric, Ez component is 0, but Hz not equal to 0. Transverse electric field, where the rest of the electric component, that means Ex, Ey and Hx, Hy are perpendicular to the direction of propagation. Or Z direction. In transverse magnetic mode, the Hz component is equal to 0 and Ez not equal to 0, and rest of the components Ex, Ey exist, Hx, Hy exist, and they are perpendicular to the direction of propagation. So we will study all these things: transverse electromagnetic mode, TE mode, TM mode, and in your waveguide we have this TE mode and TM mode. This waveguide do not support the TEM mode, and your waveguide supports TE and TM mode. In the space it propagates it in the space. After this waveguide we have an antenna. After this antenna, this is the waveguide. This is the antenna. Antenna propagates electromagnetic wave, that is TEM wave, transverse electromagnetic wave. But inside this waveguide, it cannot transmit TEM mode. Either you have TE mode or TM mode. So what is the you can see different types of modes. Actually, during the solution, while solving the wave equation, we have a solution. From that solution, we will study in the fifth module. In that equation, we have a case that sin theta equal to 0. In that case, sin theta equal to 0. If sin theta equal to 0, theta may be m pi or n pi. Right? These m and n are the integers. This m and n denotes the number of half wavelengths. M denotes the number of half wavelengths in the x direction or in the broader side. Suppose this is the broader side of the wall and this is the narrow side of the wall of the rectangular waveguide. I have told you the broader dimension. This one is the broader dimension. This one is the narrow dimension. This is the A and this is B. This is B or this is B. This one. This is the A, this is the B. So M denotes how many number of half wavelengths along this broader dimension. That means if it is 1, that means here number of half wavelength is 1. That means here M equal to 1. But here one, this is 1 half wavelength, this is 1 half wavelength. So here M equal to 2. Similarly, in this side, if there is 1 wavelength, then N equal to 1. If there are 2 wavelengths, then N equal to 2. So depending upon the number of wavelengths along the broader dimension and along the narrow dimension, we have different types of modes, and each mode has its corresponding cutoff frequency. But what is a cutoff frequency? A rectangular waveguide acts as a high pass filter. High pass filter means it allows the high frequency. One frequency onwards it passes. Suppose the cutoff frequency is 1 gigahertz. That means 1 gigahertz onwards it passes. That means 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz, like that. So we have, depending upon the cutoff frequency, we have the dominant mode. The mode which has the lowest cutoff frequency is called the dominant mode. So you can see I have just discussed that this is TE10 mode. That means here in the broader side, that is one half wavelength. This is TE20 mode. There are 2 wavelengths in the broader dimension. This is TE30 mode. There are 3 half wavelengths in the broader dimension. So M denotes the number of wavelengths along broader direction and N denotes number of half wavelengths in the shorter direction. And we'll prove that we have a derivation that in transverse electric mode, the dominant mode is TE10 mode. In transverse electric direction, in transverse electric mode, TE10 is the dominant mode, and in transverse magnetic direction, in the transverse magnetic mode, TM11 is the dominant mode. That means this mode has the lowest cutoff frequency. In this transverse electric mode, TE10, that means M equal to 1, N equal to 0 gives the lowest cutoff frequency. Similarly, in the transverse magnetic mode, M equal to 1, N equal to 1, TM11 mode is gives the lowest cutoff frequency. That means these are the dominant modes. The dominant mode. The mode having the lowest cutoff frequency. The mode having the lowest cutoff frequency is called the dominant mode. So we can have TE20, 30 like that, but they are not the dominant modes, because if you derive TE10 gives the lowest cutoff frequency. Similarly, TM11 gives the lowest cutoff frequency. That's why if you anyone asks what is the dominant mode in transverse electric, TE10 is the dominant mode, and the transverse magnetic, TM11 is the dominant mode. So basically here we have we'll do the experiment on the TE10 mode. Here we will consider the equation in the mode as transverse electric mode. So here we have a formula to calculate theoretically the frequency and wavelength, and practically by frequency meter we will calculate the frequency and wavelength. So we will try to match the theoretical and the practical value. So what is the formula? We will also derive in the module 4. Let me tell you the formula. This one. This formula for TE10 mode, this 1 by lambda 0 equal to 1 by lambda g square plus 1 by lambda c square. So let us discuss what is that. 1 by lambda 0 equal to 1 by lambda g square plus 1 by lambda c square root of. So what is lambda 0? Lambda 0 equal to free space wavelength. The wavelength of the wavelength of the wave in free space. This is the guided wavelength. That means when the wave is propagating inside the waveguide, the wave what is that in that time what is the wavelength, that is called the lambda g, and lambda c equal to the cutoff wavelength. I told you that in the dominant mode you have a cutoff frequency fc. That means that frequency onwards it passes. Suppose frequency equal to 1 gigahertz, then corresponding we have a lambda c. A frequency has a corresponding lambda c. A cutoff frequency has a corresponding cutoff wavelength. That is called the cutoff wavelength lambda c. So there is a relation that 1 by lambda 0 equal to root over of 1 by lambda g square plus 1 by lambda c square. This one. So what is the what we have to calculate? So here we have to calculate the lambda g, lambda 0. So here the unknown is this one. This is the unknown. And from the micro test bench we can calculate lambda g and lambda c. So lambda c is fixed. Lambda c equal to, for a TE10 mode, lambda c equal to 2 into a. A is this one. I told you earlier, a is the length in the broader dimension. We have measured this one. A A equal to 2.286. 2.286 centimeter. So you can calculate lambda c, 4 point something. You can calculate lambda c, and lambda g is the distance between two successive maxima or two successive minima. So in the microwave test bench, I will show you one maxima will come, then minima will come, again and another maxima will come. So the distance between two successive maximas, or one minima is there, then one maxima will come, then another minima will come. So distance between two successive maximas or distance between two successive minimas is called the lambda g. So lambda g equal to 2 into d1 minus d2. d1 is the position of the first maximum, d2 is the position of the second maximum. So you can calculate lambda g from the microwave test bench. d1 is the position of first maximum, d2 the position of second maximum. Okay, so we can calculate lambda g, lambda c equal to 2 into a. You can calculate, from that you will get the lambda 0. If I calculate lambda 0, then frequency will be f equal to c by lambda. I can calculate f. So this is the theoretical calculation of frequency. Now by this formula, theoretically you can calculate f0, and we have a frequency meter. I have told you the microwave test bench, we have a frequency meter where there are certain scales. From that frequency meter we will calculate the frequency. Okay, this is the theoretical, this is the practical. Okay, now we calculate the percentage of error. By theoretical method, how much frequency I am getting, from the frequency meter how much frequency I am getting, from that I will calculate the percentage of error. Now we will go for the microwave test bench to do the experiment. Let us go to the microwave test bench for the experiment.